What's up, everybody? This is Dan from Sage Math Tutoring. This is a video for a calculus student of mine, and we kind of ran out of time in the session for me to go over and sort of decipher these notes that she has. And this is a concept I sort of needed a refresher on anyway, but I wanted to make this video for her, but I also think it might be useful for you all as well. So let's see. The idea here is to evaluate the definite integral using right rectangular approximation method for f of x equals 2x at the interval -2, 1. So looks like my student's teacher drew the situation for the students, which is good. So in essence, you know, f of x equals 2x is certainly this slanty line here. And we're going from the x value of -2 to the x value of 1. So this is the interval. Now, the reality is that it's going to be this sort of red area, the ultimate answer of this, right? The answer is going to be that red area plus this yellow area. And that ultimately is going to be the answer. Now, there are easier ways, perhaps, of doing this than what we're about to do, but nonetheless, what we're about to do is a good demonstration of certain principles and how limits can be used and so on. So, first of all, a couple of concepts out the gate before we even dive in. If you are doing a thing where you're doing the limit as n approaches infinity, and maybe the expression you're dealing with is that, well, we all know that we can replace the n with an infinity, and anytime you have a constant over infinity, that's essentially zero. That's as good as zero. Okay, so that's one concept to keep in mind. Another concept to keep in mind has to do with this summation notation. My student's teacher likes to use the word k down here. And let's say the top number was 3, and imagine we had a 5K here. So what that means is you're going from a K value of 1 all the way up to a K value of 3, and you're essentially creating this structure where it's going to be 5 times the K value of 1 plus 5 times the K value of 2 plus 5 times the K value of 3. And then that equals, 5 plus 10 plus 15, which is what, 30? Unless I'm crazy. Okay, so that is a general reminder of sort of what this means and how it works. So that's something to take into account. Another thing to take into account is the following concept, where imagine you had k equals 1, and then maybe we go up to 4. And instead of a 5K, you just had a constant here. Okay, you just had a constant. Well, what that means is you're just going to be um, adding 5 uh, to itself 4 times. Okay, that's all that means. Okay. This is the first position, sort of corresponding with k equals 1. This is the second position, sort of corresponding with the k equals 2. Third position corresponding with k equals 3. And then the fourth position corresponding with k equals 4. Now, you might be wondering, well, why is that? That's really weird. I guess one way of looking at it, if I'm not mistaken, is because you could imagine this is like 5, let's say k to the 0. Because hopefully we're all in agreement that k to the 0 is really just 1. So 5 times k to the 0 is really that, right? So if we were to strictly follow the sort of rules, um, it would be this 4 times, right? It would be, let me just kind of cheat by copying and pasting right now. I mean, it would really just be 1, 2, 3, and then 4. And, that is the same as 5 plus 5 plus 5, right? So, um, I think maybe that's the justification as to why when you have a constant here, you're really just doing that. All right. Now, let's think about what that means, though. What it means for this structure here to equal this is that, this thing ends up equaling 5 times 4, right? Which is 20, of course. But notice how you have this, we'll call it the yellow 4 up top. Well, that's right here, okay? So any time you're doing this sort of summation with a constant, you can just cut to the chase and say that it's 5 times whatever that number is up there. Okay, so that's going to be a thing. Another thing to know is the following, and that is imagine you have k equals 1, and then maybe we're going up to 5 here. And then you just have a k here, okay? Well, that should be pretty easy to understand, right? That's going to be just um, k being 1, plus k being the next one, which is 2, plus k equaling the next thing, which is 3, plus k equaling the next thing, which is 4, plus k equaling the next thing, which is 5. Okay. And that's going to end up being 6 plus 6 plus 3, 15. Okay. Now, you know, this is really the same principle that we did in red, only now instead of 5k, it's just literally k. And, therefore that should be fairly easy to understand. However, this is sort of an arithmetic sequence type of, or an arithmetic series type of situation. And there is a formula for that, such that it's as follows. So imagine you have this scenario, but maybe you want to make it abstract and come up with a general rule. So instead of a 5, we put an n up there, and it's still this summation featuring k. It turns out that that is going to be always equal to this structure here. Now, this scenario is something that's worth memorizing. It actually has to do with an arithmetic series. This is sort of the arithmetic series formula applied to this situation where the first number happens to be 1. Okay. However, rather than getting into why that is and diving back into that, I would encourage my student and me to memorize this. And we could put it to the test right now. So imagine in this previously mentioned red box situation, we had done n times n plus 1 over 2. Well, n is 5 times 5 plus 1 over 2. And that would be 5 times 6 over 2, which is 30 over 2. And that is indeed 15. So that would have worked there. So really, these are concepts that are worth remembering, certainly. One of them is that anytime you have infinity down below, that becomes a 0. Understanding generally what this summation notation means in general is helpful. If you have the summation notation along with a constant, it really ends up just being that constant times whatever number is up top. Okay, and if we were to generalize that, I think you understand that that would become the following, where it's k equals 1, you have n, and then if you had, well, I guess we're not generalizing, we'll call this 10 as a constant. So that's going to become 10n, all right? So that's for sure. And just this is a nice reminder of what happens if you just have the variable k here, it really ends up becoming that. But the generalized structure that we can rely on for this type of situation is this. So let's decipher what's even happening here. Um, First order of business is to recognize that when you're doing a right rectangle approximation method, specifically for that scenario, you should understand what delta x is, and you also should understand that you will be dealing with f of um, the starting point, starting, we'll call that the starting x value, plus, and in this case, we'll use k times delta x. You're going to be dealing with that, okay, as well. Now, delta x is going to be b minus a all over n. So these are sort of things that you need to remember specifically for this double R RAM situation. Now, the -2 is your so-called A value, and this 1 is your so-called B value. So it makes sense that the delta x is going to be 1 minus -2 all over n. That's what this is saying. And that does indeed become 3 over n. So you're going to need that. Now, as it pertains to dealing with this f of blah, okay, the starting x value is this. It's a, right? So that's going to be -2. And that's why the teacher emphasized this right here. Okay. So it turns out that for this particular problem, the function could be represented as -2 plus k times delta x. So squaring away this yellow box information and squaring away this yellow box information is going to be crucial for this type of problem. That's the first thing you should do. Now, ultimately, I feel like this should be the sigma notation right here. Like this is going to be the answer with an n on top. Okay. So essentially, what you'll be doing is this sort of summation where it's that function thing times the delta x, okay, times the delta x. Now, it's true that this red box part or this red bracket part is really equal to that. Because if you think about it, f of blah, that really just means substitute blah in for x. So then you end up with this. Okay. So what I'd like to do now is pick up from here. I don't want to like just point at the notes because I might not even be crazy about how the teacher went about this. But for my student watching, just know that after we talk about how to do this, all of this will be understandable. Okay, so let's take a look. It's true that we can take this delta x, and in fact, you should always, when doing these types of problems, take the delta x and put it on the outside. So let's go ahead and do that. And the reason for that is because that delta x is ultimately a constant, and you can do that when you're dealing with constants. So we have this, and then we have our situation here, right? And at that point, I think my student watching understands that you can distribute this, which is going to make it a lot nicer. And as a result of that, we would end up with -4 plus 2k delta x. Now, the next move is kind of interesting. We know that it's sort of ultimately this delta x times this whole thing, right? In fact, maybe it would be better if I wrapped parentheses around this to really communicate that we're doing this sort of summation of this entire quantity there. So it's going to be delta x times whatever that result is. And I think my student watching understands that that can sort of be split in a way. You can actually split that such that it looks like the following. I'll actually keep the brackets here. So it would be the summation of just that -4. All right, I'll put that in parentheses, plus the summation as it applies to this, 2k delta x thing, right? Now, let's go step by step and really think about what that is, right? Well, hopefully we're seeing that that -4 thing due to the earlier concept that I had mentioned, that's just going to become -4n, right? So this becomes that -4n. Over here, I guess we could kind of do, yeah, we could take the 2 and the delta x out. So I'll do that right now. I'm I am trying to keep it somewhat close to the way the teacher did it. Um, the teacher do it that way. Yeah, kinda. Yeah. It's just that the teacher kind of like skipped steps to go from there to there. So this is self-explanatory, but this there's like kind of like several steps that you could have at least mentioned there. So let's take that 2 times delta x out. Now, let's also just be very clear for my student watching. This is really three numbers getting multiplied together here. You have a 2 that's getting multiplied by k, and that's also getting multiplied by this other number, right? So in a sense, we have actually three numbers right here, right? And you don't have to draw these parentheses, but I just want to make it very clear that this is indeed three numbers. Part of the reason I'm saying that is because the delta x can be kind of confusing. We're not used to seeing that, but it's important to recognize that that's just some number. And in fact, we kind of found an expression for it earlier. So this is 2 times delta x, right? And that is going to be such that we have this with just a k there, right? Well, hopefully we're seeing, due to the previously mentioned information, that that k right there part, that whole thing, namely this situation, well, isn't that just going to become that n times n plus 1 all over 2 thing we had talked about before, right? So hopefully that makes sense. And then what the teacher is expecting is for you to sort of clean that up. And how would you do that? Well, you would acknowledge that these twos would cancel. And then you would be with this delta x times n plus 1, right? And it kind of seems like the teacher wants you to save the substitution of 3 over n for delta x towards like the end. Okay, so it's like you keep the delta x until like a certain moment. You clean this up maybe. But right now, we can remember that any time we see a delta x, you could hypothetically replace it with a 3 over n. So that is indeed what we will do right now. So we have this, we have a 3 over n. We have a negative 4n, that's still there. Plus 3 over n times n plus 1, right? And I think we can all see where that's going. So at that point, we are looking at this. However, you would indeed be canceling the n's, and then you would have this 3 times n plus 1. And next thing you know, you could simplify, right? You could simplify negative 4n plus 3n plus 3. And as a result of that, of course, we will end up with the negative n plus 3. And after distributing the 3n into that, I think we can all agree that's going to become the limit as n approaches infinity of negative 3 um, plus, what is it, 9 over n? Okay. Now we're ready to substitute that infinity symbol in there, and that's going to become 9 over infinity. We all know, hopefully, that that's negative 3 plus 0 due to the previously mentioned concept. And then, that's what that is. So notice, by the way, for my student watching, when you're doing the limit stuff, the moment you substitute the infinity symbol in there, that's the moment where you can actually drop the limit notation. Okay. So that is a lot. For my student watching, if you prefer the way I did it to the way your teacher did it, you can go ahead and take some screenshots. So I'll just kind of, let's say, leave this here for a moment. Go ahead, screenshot that. Pause the video if need be. Um, Go ahead and, if you want, screenshot that if you want. Okay. Now, with regards to the way your teacher went about it, let's just make sure we understand what's going on. So we have the 2 delta x. We did that. We also did that, I think. Yeah, the negative 4m, we definitely did. And the 2 delta x is the blue underlined stuff, whereas the k is the yellow underlined stuff. Um, you had performed a summation on this expression, and that's why when you do the summation of k, it turns into that. This n canceled that n. We did perform that move. We also performed this move. So as a result of that, it should, in the parentheses, be negative 4n plus 3 times n plus 1. Hopefully, we're in agreement about that. Now, with, the 3 over n on the outside, now this is the green parenthesis. This is the green parentheses. So this should be the green parentheses, but let's see if we agree with this. Negative 4n. So I don't know if I agree with this move here. I'm not really sure what this is about. So I don't know if I resonate with these 2 lines. Now, I could be missing something. I do resonate with this. Um, because like you could distribute the 3n into that, and I think you would end up with the blue box, right? So 3n times that negative 4n, well, that will be negative 12. So I'm happy with that. And then we have 3n times that. Well, that's going to be 9 over n times n plus 1. And that is this, right? So that part I'm on board with. Again, maybe I'm missing something here. Um, now, we just went about it a little bit different. I simplified all of this first, right? Hopefully my student realizes that. And by the way, I think you should do that. I mean, that's like PEMDAS. And then we have this. Okay, well, I think the teacher said, "Oh, let's plug in infinity now." Well, that would be 9 times infinity all over another infinity, right? Because infinity plus 1 is really just infinity, and infinity down here is just infinity. So that's like infinity over infinity, and that's just like 1 basically. So then your teacher treats that as negative 12 plus 9, which is negative 3. So that could have been another way of going about it. I mean, I like my way better because I used PEMDAS, and PEMDAS is like what you're supposed to do, you know, I think without exception. So all of this, simplify the green brackets, simplify the green brackets. Now we're ready for the distribution. But anyway, hopefully that is helpful. Obviously, for my student watching, doing a few more problems like this is going to be a good idea. All right. On your own and just making sure you get it. All right. Well, hopefully that was helpful, and I will talk to you all later. Take it easy.